Welcome. Today I want to demonstrate how to actually take the measurements and do the configuration to an OpenSCAD project which you can use in your 3D printer to print such an inlay for your Ratchet box. So actually you can see we can construct relatively complex things here. You have a measurement then for, in this case, our 11mm long hex nut, and all this fits quite well down there. You also see the numbers for the sizes, and as you can see also a second part can be glued then to this. It's actually a model which we have which models everything. You set it up and you can break it down then in your slicer or possibly in OpenSCAD to print it in pieces if your printer is not capable of printing inlays of that big size. So what this video is about is actually taking the measurements on the things which we see here, and then by this you should be able later on to also set up a project to print your own inlay.
The journey normally starts at the software, so the first thing you have to do is you have to install OpenSCAD. OpenSCAD you find on this internet address. You can go to the downloads page and install the version for the operating system which you use. And after the installation, we need a special library from the OpenSCAD page. So you have here on the file and showing the libraries, you have a folder. In the end, you have to have this BOSL2 library, which you can actually download here from the OpenSCAD page at libraries. Here you will find the BOSL2 library if you click on library. So to install this library, you go to code, scroll down, you download the zip file, and after you have downloaded the zip file, you have to extract this into the directory which OpenSCAD opens when you go to File, Show Libraries. You have to take care that you name it exactly like this, so you have to ensure that the system can find it. After that, you have to restart OpenSCAD and you are good to start your first project. Starting the first project means you have to get the files to generate the Ratchet box. So you either get this from the GitHub repository or from the Thingiverse page. The newer files are always available on GitHub. So in GitHub you can go to code, download zip, and you extract the zip file to whatever folder you like. This will then look similar to this structure for the Ratchet box, and you can go to the source folder, and in this you find an example file with a relatively complex structure, the empty template, which you can take as a starting point, and you usually take a copy of this like I did here already, and we will modify this copy now. So you should do a copy, and from the copy you can then start to edit this. So the copy you can open here with File, Open, and you can see already that I did already some first steps in the adaptation of this. Your first view will be from the empty template and look like this.
In the template there are 3 different types of objects which can be modeled. That is actually a borehole for the normal hex nuts here. So that is the most simple form. Then we have what we call continuous tubes or laying hex nut actually, which can model either these extensions here or the longer hex nut like this, including actually changing diameters along the way. So by this we can also model then this more complex shape here, or even this one. These, that should all be no problem. And the most complex shape is actually for the ratchet itself, that consists actually of 2 circles and even a more complex form for ratchets like this, which have a circle here for the head, a circle surrounding actually the actual drive shaft, and also then you see here a half circle which can take actually this mechanism and these sides and get the room for this. So, and if you look at the modeling process for the ratchet itself, it consists of these boreholes there, and actually then again same mechanism. You have more or less different diameters for something that is assumed to be round from the point on here. So let's go into the details of all these 3 things. Let's have a look at the most simple one. That is actually the borehole for the hex nuts here. So if I take any of these, you're taking actually the diameter reading and the length of all these hex nuts. And it's important to note that this is first of all your reading, and later you have to add sufficient amount of diameter so that in the end you're able to easily take it out of your inlay.
So once you have taken all the data for your boreholes and you have taken the measurements at your hex nuts, you will fill in this data here in the borehole lists. So you can have as many lists as you want later, and we will also have a look at how they are processed. So each hex nut gets an entry like this, where the first number, the 42, actually gives the diameter of the borehole. The second gets the comment that is written on the bottom of the borehole, and this is the length of the hex nut, and this length is later taken to have equally a topmost position of all hex nuts that are there in the box. So when you see, the first one is the number with the 32 here, and the last one is the 12. So actually this list gets processed to here. And we have a second list here, the 3/8, then 10 and 11, that is my adapter. So that is along the y-axis. Once we have defined now all our borehole data, we want to position them. So, and I decided now to put these boreholes at the top here. So, first of all, at the very beginning of my file, I defined my box width to be 400 and the depth 200. So this is the width, that is the depth. We have a box height of 45 at the moment planned, and the base layer should be at 27 later on. So if we tilt this, then you can see that from this corner to here, these are the 27 millimeter, and the height is 45, so above this. So all hex nuts that are later put here inside are aligned in such a way that the topmost position of the hex nut ends up 1 millimeter below the box height. The most complicated part is now to position the objects which are drawn along the x-axis or y-axis here. So to position them in the box where you want them. So for this it's fundamental to understand first of all the coordinate system. So we see here the coordinate system of the into that direction on rising x. Here from the origin, the rising y-axis values, and finally the z-axis. So what you have to understand is if you want to move this to the right, you have to increase your x value. If you want to move it toward that direction, you have to increase the y value. Normally, the z-axis here would not translate because the script is made in such a way that it calculates the optimal z value automatically. So you would actually destroy this calculation if you modify the z-axis. There is only one value to configure there, that is for the ratchet. But so and if we want to move this now from into these directions, then we actually translate whatever is really drawn here. So let's focus first of all on these three elements here, on these three boreholes. That is what we have defined in this borehole 2. And you have to see that the boreholes are actually generated from what all I have selected now in the editor. And then we see here the trends for the x-axis so that this thing is to the y, and 0 in the z, because that is automatically taken care. And what does it shift by 50, 60? Everything that it is in the curly braces here, which are selected. So actually this block. And this block draws the three boreholes. It's a very fundamental concept which you need to understand. So if we look at the boreholes here, these process now the boreholes 1, that is the long list, and it's to the right, and you see there is no translation given here. That's why this is really in the 0, 0, 0 position. So x is 0, y is 0. So not shifted at all. So now let's see what happens if we look at it from the top. So the idea is now to move all these things here to the top. So the first idea is, of course, I shift this by x stays 0, so it goes up. We remember this is around 40, the diameter of the 32 millimeter borehole here. So we want to shift this by 160 in the y direction and 0 in the x. So what we do is we say translate, and then we say 0 in x, 160 in y, 0 in z. And what do we translate? It starts here and it ends here. So everything that draws actually the boreholes. And when we save this, we expect that this gets shifted. Well, yes, it did that a little bit too far as we see, so we can fine-tune this, say 150. Okay, pretty neat. Well, now we see we will actually lose a lot of space here if we do it like that. So that's not what we want. So what we want is actually that this line, which is having equal distance to the x-axis, actually is here at the top. So that the smaller ones get to the left and the bigger ones to the right. So how can we do this? How can we achieve this? We need to rotate all this. So how do we rotate? Well, remember the z-axis is coming out of the picture at the moment. We look at it from the top. So that we need to turn it around the z-axis. And our turning point is here. That's the 0, 0 coordinate of all this block, more or less. And this is the origin of everything. So 0 and 150 shifted the origin to here. Now if we turn it by 180 degrees, we expect them to come here. Let's see whether that really happens. So what we say is rotate, and then we say 0, not around the x-axis, not around the y-axis, but by 180 degrees around the z-axis. And then what do we want to do? We want to do this for all this that draws the boreholes. So what happens if I save this? Well, it's vanishing. Is it really vanished? No. How do we find this? We scroll down and then we see here an if false and some comments that tell you that this is a useful setting for debugging. If you set this to true, you get a different view of everything. Now the object that earlier holes in the plate are now positives. And if we look at everything now, then we see that this is now doing the right thing in the wrong position. So it's parallel to the x-axis, this line here. That's how we want it. But our box is actually here from 0 to 400, respectively from 0 to 200. So, and it turned it around, so our center point is here. And we need to move the center point now to the topmost right position, which is 400, 200. Or other way around, it is box width and box depth. Let's see. So we now translate by box width, which is the 400, and box depth. If we save this, yes, it gets moved and it is now there. If we go down now again and switch this if again to false, and save this, then we see we have achieved what we wanted. The position is as expected. It's topmost right here and all along. So it's too near now to the borders to really 3D print it, but that is easy to achieve with a box width -2 and box depth -2, and we save it, and there we are. Positioning like this is a universal concept with translate and rotate. Normally you always first translate, then rotate, and then draw, which actually means it's the other way around technically. But that should not matter too much. If you stick to this order, you should be able to rotate things and translate things relatively easily, and you should be able to put everything into useful positions. So let's see, I want to put these things now here alongside this. So I can move this, say, to 0, 120, and then we see it's overlapping already. So maybe 110 is a better value. No. That's better. And say 2 and 104. That's quite good. And we zoom in a little bit. Possibly that is right and what we want. By this we have managed to position everything as we want. For your convenience, there is this borehole calculation along x-axis and along y-axis. Technically speaking, you could do everything also without this, but okay, this is for the convenience. After we have positioned the boreholes now, the next concept that we have to look at is actually how to measure and how to model extensions or the laying hex nuts, so the long hex nuts which can't stand in a borehole.
The more complex form is actually on such things like here. So as I told already, this piece and also these pieces here are all modeled in the same way. So let's have a look at this one. So what you need overall is of course the length of it. So you're going to have a measurement for the length, which is actually then your end length in the end. Then you have to decide where's your start or end. This is more or less an arbitrary decision. For me, I do start here now. So that means I have a diameter of around 23 millimeter at the position 0. So 0 is here. And I also have this diameter still at a distance of around 21 millimeter. You see, I take a little bit more. So 21 millimeter still gives us the 23 millimeters of a diameter. And then at the distance of 27, we are down to around 15 millimeters. Next step is actually to measure this distance. We are at 99 or 98, still this diameter of 15, and then we have a diameter of 17, also here, till the final length of 125. That's it, these measurements you require.
How do these values get into the model now? I define two extensions now. So the one which we saw in the video is 125 millimeter long. So I named it 125, and as measured, we have at position 0, that is here, actually a diameter of 24 millimeters. As we have it here, at the distance from the 0 starting point, 21, we have a diameter of 24. Here is 28, and at 28 we have a diameter of 16. Then there is no change to a diameter of 99, where also we have a diameter of 16, and at 99.1 we have a diameter of 18. As we have at 125, still 18. So, and this defines actually what we require here. How do these data go into the model now? So we have the horizontal hex nut function, which is used for everything that is modeled as a flat thing into the box inlay. So we have the X position and the Y position here. The X is here the starting point, that's for sure, and the Y position is the middle of the axle, so the middle of the tube. So, and then you have here the parameter to rotate everything. Please keep this 90 unchanged. If you set this to 0, the object will point at you. So, and if you want to turn it, you might put here something like a 90, then it will turn to the left around this position. So you could also say 45, that is fine, no issue, and you get it like this. And here you give the name of what you have defined. So in this case the extension 125. So with this modular you can repeat the same, you can give a different position, you can give a different rotation with different data, and then this is modeled. After modeling all the horizontal laying hex nuts now, I want to show one special example where it really makes a difference from where you define the zero position. So this is actually the model for a typical 1/4 inch to 1/2 inch drive shaft, so something that you put into your drill, your cordless drill, to rotate or to turn actually a hex nut. And if we zoom in, then you see that one time I defined this position as 0 going up, and this time here the same is defined inverse, and this is the 0 position. And this has an influence on how the characters and how the text really appears in the final object. So I guess that this one is the better one, so this one I will throw out. So, and of course you see this here in the left in the list. Extend this a little bit, then can remove the first line, save this, and the not so optimal definition is gone. The final object to model is now the ratchet, and we have to understand what the arguments for the ratchet are and how to measure these.
The most complex thing is of course the ratchet itself. This ratchet, for this actually everything goes from the center turning point here, the measures, and you are supposed to measure first of all circumference here, the diameter here, 43 millimeter around I would say. And then you need actually, the second thing you have to know is everything counts from the middle of the handle. So you need the depth of this. This is 20 millimeters in this direction, so from the middle it will be around 10. Yeah. So your depth for the diameter of the head of 42 is actually 10. That should be okay. And then you have this depth of 35. As we know, we have around 10 above this. So the second bore will be 25 millimeters from the middle here of this axle, of the handle axle, to the lowest point here. So around 25 millimeters, maybe we take 27 in the end, so that never comes into any problem. So, and for this of course the diameter shall be measured like this, get a round hole, so around 18 millimeters should be good for that. That is to model the head actually. If you have a more complex form of the head, like for this ratchet here, where you have actually also another half circle here, that is what you can model with the pi, the extra pi. Otherwise you set the pi to a radius which is around 1 millimeter, so that this doesn't come to any real effect. But also that is foreseen, and then you can also, depth again is from the center point to the lower end, and the radius is symmetric there, that the angle is symmetric in the script, and diameter is the outer diameter. So modeling the handle again is simple. The point is here the turning point, so what we are going to measure is actually that we need here a measure around here, that is our 42, so that's around 0, and we see this is going down till here, say to 35, at a distance of, from the middle, around 32. So if we say that at the distance of 32 we have then a measurement of around 35, that's how we will model it, so that this goes down linear to here. And at the offset 0, as I told already, it's around 23. We will take the same half of the same diameter here that we had actually for our circle of the head. So then next measurement will be around here, so we see around 15, and again that is at 50 millimeters, so it will go down like this, and this goes till here, so still our 15 millimeters, and we need this for 138 millimeters around. That should be good. And then another measurement, that is here, oops, that's around 20, say 22, 21, 22, and that is now clearly at a distance of 141. So what we are going to do is actually within, say, a millimeter or half a millimeter, we will extend this with a command and with the values to model this, and so on and so on. So you go in the same way till the very end to handle this. It doesn't matter how many measurements you take, you can have really complex forms. This is much simpler than this is. I guess for this these are around 20 different measurements, so quite a lot from modeling here till the end, but creates a perfect fit if you are really on the point there.
Again, the final thing is to take the measurements and bring it into the model. And we have here a function called Ratchet. Again, we are in the module inner bodies here. So, and as usual, we have first the X and then the Y-axis position, and this is this point here, 350 times 110. So if we look from the top, we can easily see this. So then we have a rotation here at 180 degrees. So again, if you want to turn it around, then after updating this, you see it's turned around now around the center point and moved the other handle to the right. So anyhow, I reverse this or revert this, and we get our model here. So then we see the next argument here, the 18 and the 27, is actually the depth as measured before. So we have a diameter of 18 millimeter and a depth of 27 here in the center. Then we have a diameter of 44 and 10 for this circle, and the pi actually is not used. So for the demonstration what this does, I exaggerate this a little bit now but that should be should demonstrate the thing. So like this, you get such a thing. So from here, this is your middle. So half of 270 degrees go to here, half of 270 degrees go to here, at the moment at a depth of 20. So for the current ratchet, this is not required, so I simply put it to such a small value that it would be in the inner of both of these circles, so then it doesn't matter at all. So this parameter needs some more explanation. This is actually giving of the handle, the middle axis of the handle, how deep it is below the surface. So, and if we tilt this now, then you can see how deep it is lying inside the case. We can have a look at this a little bit later again. And first of all, these are the handle data now, and the handle data model actually this part. So if we go up, we see here the handle data, and we see at offset 0 from the center point I have a diameter of 44. At a distance of 36 I have a diameter of 37. Then at a distance of 49 I come down to 16, and so on till the end. So that should give you an idea of how you can model this. So the list can be long, that doesn't matter. That's all more or less what it takes to also form a complex shape. It might also be useful to increase in the middle here something. By this you would get a point where you can grasp the handle easily out of the box. Depends on what you like. So then we should concentrate once again on the depth of the thing. And what you can see here, it's 5 millimeters below the surface. Once again, put this a little bit to the side. So if I put here 9 and save this, and you see that this gets deeper. But also you can see, if we look from the top again, that we have now a through hole that would be too deep. So 5 in my example is now a good value because it is just not dipping through, and we have it fixed really in this. We are now near to the end, and I wanted to show you one thing what can help you during the design. That is also here documented, that you can uncomment this translate command here, which gives you then an impression about where the lid would be of your box, so that you can get an impression of the situation there, and you see then actually how all comes together in the end, so, and how that would be. If you comment this again, this vanishes. Often it is more useful to have a look at the positive structure. So you set this false again to true, and as you know, then if you save this, you get more or less here where are my boreholes and how is this all modeled. So again, if we look from the top, it looks like this more or less. There is a difference actually for these different things. You see this one, that's now interesting. You see actually here a different structure than to this. The reason for this is that we can actually show this if we uncomment this line. Then if we look now from the side to this, then you see where is our base layer. So this will be the base. The boreholes are below this base. See that the big diameters have their center below the base layer. And by this, there is a box modeled onto this automatically so that you can take it out. So imagine your center goes down and we would only take a cylinder here, then your 3D printer would print something here, and that's why for everything where the cylinder is below the surface, the center of this is below the surface, we have such a box here. And you can also see that for this one, because it has a small diameter compared to the other ones, the center is above this. And then this block is not modeled. So what you can also see now, if you uncomment the second line and save this, is actually where your lid would be. So, and you see now how this all goes together and how it gets modeled. You also see that at the moment the handle of our ratchet itself exceeds more or less the lid. The reason is that our handle is in this concrete case relatively flat. So you have to check whether the center plus what it has below the center and the space you have left above, whether this will close in such cases. So really check thoroughly whether everything is plausible before you go for your, I don't know, 20 hours print or whatever this may take on your 3D print. Hope this was helpful and informative, and good luck in printing your own Ratchet Box Inlay.